Alright, let's talk about peroxygens. Hydrogen peroxide is the most common form. Okay, they are known as active forms of oxygen. Hydrogen peroxide is H2O2, and generally speaking, in the amount that we use for antisepsis, it's not toxic to humans because you have an enzyme called catalase that breaks hydrogen peroxide, H2O2, into water, H2O, and oxygen, O2. No, that's not a balanced equation, but you get the idea. So that's why when you put hydrogen peroxide onto a cut, it bubbles. If you use it for an oral mouth rinse, you get a mouthful of bubbles. You've got a mouthful of oxygen. So how would this be effective against certain types of microbes? Your oxygen-sensitive microbes are killed by hydrogen peroxide. They don't have the enzymes to deal with it. Okay? And a lot of your pathogens, to a certain extent, are sensitive to oxygen. Also, when you have oxygen wandering around in its active form, it has a tendency to steal electrons. So it acts like your halogens. Steals electrons, disrupts enzyme function, disrupts membranes, all sorts of good stuff. Now, the problem is stabilizing it. Peroxides are not known for being terribly stable in the presence of bioburden. Now, from part 1, remember that bioburden is anything of a biological nature which your disinfectant or your physical control method has to kill through. So, if you're trying to clean up saliva in a dental office, dental operatory, with a hydrogen peroxide containing disinfectant, what's in saliva? Catalase. Breaks down the hydrogen peroxide, and it renders it ineffective. Now, recently, within the last 8 years or so, they've been able to stabilize these peroxides, these radical forms of oxygen, so that bioburden doesn't break them down, and they're able to kill on surfaces for a fair amount of time. And we're going to be seeing more of them because peroxygens are actually highly effective. They're nearly as effective in killing microbes as the halogens are. Now let's talk about surface active ingredients. Soaps and detergents are considered surface active agents. They are, and let's bring up my picture of the soft soap, without the phenolic in it, without the triclosan, the soap itself is still effective as a microbial control agent because the detergent breaks up oils. It also cleans. So it physically removes organisms. Now, you can have a lot of microbes very happily living in your container of soap or on your bar of soap. But when you physically remove them from your surface or from your skin, it's what we call degerming. And this reduces the number of organisms. Okay? So when you've reduced the number of organisms, you still achieve the effect that you want. So we have a tendency to use soaps and detergents in our cleaning agents because in the process of cleaning, we're reducing the organisms. Now let's talk about quaternary ammonium chloride compounds. This is wet. Here's your ammonium ion. This is basically ammonia that you would use in Windex, and we've attached other stuff to it. This increases how long they're able to be active, decreases the amount of time it takes for it to evaporate, and it makes it so that it lays down very nicely on countertops. Now, we have a tendency not to mix quats, as we call them, with soaps and detergents. The soaps and detergents can inactivate the ions that are going on here. But quaternary ammonium chlorides, quats, are very good at cleaning as well as disinfecting. So you're removing dirt, you're degerming, but also your quats are also popping cell membranes. They're disrupting cell membranes, and they're very effective at that. They have low toxicity to humans, and they have a pleasant smell. So we have a tendency to use quats an awful lot. In food service situations, Clorox wipes do not have chlorine in them unless it says has bleach in it. Lysol wipes do not have alcohol in them. They have quats. They're very good for use in the kitchen. They're very good for surface cleaning when you're going to have food preparation because they have very low toxicity. Now the quaternary ammonium chloride that I want you to remember is Coverage Plus that we've been using in the lab. That is a quat. It's a lovely quat. Now let's talk about heavy metals and their compounds. By this we mean salts of heavy metals. Now by heavy metals we're talking about lead, which we never use as a surface disinfectant because of its high toxicity. Silver is very good, has low toxicity to humans. Copper can be used, and mercury. Let's talk about mercury. Mercurochrome, you guys remember mercurochrome? Mercurochrome has just a little bit of mercury bound to a protein. And they also toss in some bromine, and I don't know if it's the mercury or the bromine that makes it that nice red, but I remember from my childhood, I just would much rather have mercurochrome on my cuts because it made it look like the cut was much worse. I was competing with older brothers. And so it made it look like you were a bloody mess by the time you got done. It stung, but alcohol stung, and you didn't get the war wound look. Okay? But mercury and other heavy metals bind to the active sites of enzymes and inhibit their use. Now, you're probably going, why in the world would we ever use mercury in anything? Because mercury has gotten a bad rap. It's also, in high quantities, a neurotoxin. But in smaller quantities, generally speaking, it's not a neurotoxin and it still inhibits the growth of microbes. But because of the brouhaha around mercury in vaccines that originally was linked to autism. By the way, it turns out that the doctor who did that original study didn't use enough subjects, and he was also working for a company that was trying to market their new line of mercury-free pediatric vaccines. He basically falsified his data. So anyway, but we are still very careful with mercury because it is neurotoxin. That's also why we don't use lead. Besides, by the time you get high enough quantities of lead to kill microbes, it's toxic to humans. Now with the others, silver-containing compounds, there are silver drops and creams that are put into the eyes of newborns. And this was to prevent gonorrhea transmission during travel through the birth canal, picking it up from the mother basically, getting into the eyes of the newborn, which would later cause blindness. So we would put these silver-containing compounds in the eyes of the newborn, very low toxicity, and it would kill the gonorrhea. And it made it so that the babies had little black tears. Also, silver shows up in creams for burn patients because it's highly effective against Pseudomonas. It's one of your more resistant gram-negative organisms, which is a real problem with your burn patients. And copper is, if you're using an anti-algae agent in your decorative pond, it's got copper in it because that inhibits the action of chlorophyll. Now, up to this point, all of the chemical control methods that we've been talking about have been strictly for disinfection or sanitization. Remember the definitions? Disinfection, you're lowering the total number of your starting number of microbes by 3 logs. You're knocking 3 zeros off of their numbers. Sanitization is anything that's less than 3 log reduction. Now we're moving into chemical disinfectants, or chemical control methods that can also sterilize. Let's talk about the aldehydes. Generally speaking, we're talking about glutaraldehyde, but formaldehyde is also an aldehyde. And what is formaldehyde famous for being used for? That's right, is an embalming fluid. That's preserving the body for up to a week or more so that you can have a funeral at a convenient time, so that you have enough time for families to come together and have a funeral before you put the folks into the ground and bury them. This actually started out during the Civil War when people were concerned about getting the soldiers home to their families instead of burying them far away from home. So formaldehyde. Glutaraldehyde is a little bigger molecule. If you're in the dental industry, you're familiar with glutaraldehyde as a cold sterilant. If you've got instruments or things that can't stand heat or are sensitive to water, you put them into glutaraldehyde and you soak them for up to 8 hours. Generally you leave it overnight. You may as well. You rinse it off good, and it was sterile when it came out. Unless you rinse it with sterile water, it's not sterile anymore, but you've killed all of the human acquired microbes of, say, the dental instruments that have been in somebody's mouth, and you don't have the rusting that you would see from putting it into an autoclave. Now if you use aldehydes for shorter amounts of time, you disinfect. Now aldehydes are interesting in how they act to control growth, in that they cross-link proteins. They basically freeze them into place. Enzymes, if you remember back to chapter 5, how do enzymes work? They work by moving. They close over the substrate, clip it, or smush them together, and then they open back up and they're ready to go again. Well, if you freeze them into either the closed or the open position, you've killed your enzyme. You can't use it anymore. Say structural proteins that need to move, like flagella. If you freeze them into place, they can't move. Kills the organism. And it's also a good way to preserve them for looking at them under the scanning electron microscope, because you can pull the water out without creating little microbial raisins. Okay, so that's what I want you to remember. Glutaraldehyde is generally what we use. Formaldehyde is also used. Those are your aldehydes. They work by cross-linking, and they have a little higher toxicity. They recommend that you use them in well-ventilated areas because you really don't want to cross-link your lungs.